Afternoon. Just 1 second. Everyone can hear me online? Yeah. Okay. All right. Great. Okay. Thanks for joining us for our second to last session. This is odor and corrosion control and collection systems, a case study from looks like Alberta to BC from David Speed. David Speed is with BioMaxx Environmental. Dave is a professional mechanical engineer by training. Dave has worked in the water and wastewater treatment field since the early 1990s, providing chemical treatment programs and field engineering support at municipal systems of all sizes, from major systems in Northern and Southern California, towns and cities across Western Canada and the Pacific Northwest states, and major industrial facilities, including gas and chemical plants and pulp and paper mills. In addition, excuse me, Dave led the design build group for major Canadian utility and has consulted over the past decades with a variety of smaller water technology companies. Dave joined BioMaxx in June of 2021 and is actively working with the company's customers to help them manage their odor and corrosion concerns in municipal treatment systems. As part of this work, Dave has created an innovative corrosion monitoring tool that is being deployed at municipalities across BC and Alberta. So please join me in welcoming Dave Speed this afternoon.
Thank you. I don't like hearing that since the early 1990s because it just makes me feel old. Thanks everyone for coming. I was sitting through the last talk and I have to have an admission right up front. I have no references to in-laws or family eating habits. So hopefully we can get through without those. So what I wanted to do today is I'll just talk to you really quickly about who BioMaxx is, and then talk about odor, what it is, corrosion, what that is, and the next item on the agenda there, hydrogen sulfide, kind of gives you the clue about what causes some of those. Then we'll talk about how to test and characterize the data in the system to help develop treatment options. And then we'll get into a couple of case studies. And if it goes the way I planned these, I have some time for questions at the end as well. So BioMaxx, we've been working in the wastewater field for over 16 years. We work across Western Canada and Atlantic Canada. There's kind of a black hole in Quebec and Ontario for us, but that's okay. My part of the business is Western Canadian in focus. So we do a lot of municipal wastewater treatment, odor and corrosion control, also field engineering support, that kind of thing, and a lot of data monitoring and helping people solve the odor problems they have. So odor is, it's a tricky thing to talk to people about because we all know what odor is, but everyone's nose is slightly different. So, you know, if I go into a plant and talk to someone who's worked in a refinery for 30 years, they might not smell anything because they've worked in a refinery for 30 years, whereas I might walk in and go, oh my God, what is that? So that's the problem with odors, that we all know what they are, but they're typically compounds that stimulate the olfactory organ, which is your nose. And in a wastewater system, what we typically see are things like H2S or hydrogen sulfide, mercaptans, dimethyl sulfides, ammonia, nitrogen-based compounds, and then volatile organic carbons. We see those compounds at different stages in the wastewater treatment process. Some of those latter compounds we see more in the wastewater treatment process. But what we see typically is hydrogen sulfide is the bad actor in the collection system, which is the focus of what we're talking about today. So corrosion. What's corrosion? So again, everyone knows what corrosion is. It's basically deterioration of material, usually metals, by either a chemical or an electrochemical reaction with the environment. This particular slide here, the background shows what we see as the result of corrosion, but what it is, it changes throughout the system. That particular example, which is rusting, which is iron oxides, that's probably the best known example of corrosion that people are familiar with day to day. Collection system corrosion, when we take it to the next step, there's two major contributors in the collection system. So there's hydrogen sulfide, which can be driven by sulfuric acid, which is aggressive to metals, a lot of steels, especially iron-based compounds. We'll get into some of the detail of that in a little bit. If some of that H2S-related corrosion causes pitting by its nature can be very quick and aggressive and can really start causing damage rapidly if we don't know about it. The other kind of corrosion we have in a collection system is just water related, because we got this big closed pipe, there's moisture in it and there's metal in it, and so we just get general rusting. There are ways that we can tell about what type of corrosion is present in the system. We can talk about those in a little bit. The end result of the corrosion we see, this is a pretty good example. This was a force main that had a leak in the force main because of corrosion in the reinforcing steel. The clicker has got a mind of its own here. So there was reinforcing steel in the concrete that broke through corrosion. That caused a leak in the force main and then ultimately created a sinkhole, and then you get this nice event happening, which is not a lot of fun for any utility to deal with. So when we look at the root cause of all these odor and corrosion issues that we just briefly touched on, the root cause of those is primarily H2S or hydrogen sulfide. It's obviously a safety concern for workers, for residents who live around those kind of systems, and it's also a big problem for the infrastructure's asset life. So H2S, what is, you can see from the chemical formula, it's 2 hydrogen and 1 sulfide. And why is it a problem? So as you can see here, the real challenge with H2S is that it smells, it's got the rotten egg smell. I think everyone's probably familiar with that. It's present and we can smell it at really low concentrations, typically less than 1 ppm. As the concentration increases, it becomes more toxic to people. So you get eye irritation, you get breathing problems, then you get coughing, headache, nausea. That's up around 100. I would argue even before 100 ppm that's a problem. The real problem with H2S is beyond around between 100 and 150, I think it is. We become immune. Immune is not the right word, but our breathing passages, we become sensitized to what we're smelling. So you could then, if you were in an environment that was like up in this level, you could stop smelling it basically, and then you could think, oh, everything's great, and then 10 minutes later you're lying on the ground looking at the sky. So it's a real problem with H2S, and as a result of that, WorkSafe organizations like WorkSafe BC and WorkSafe Alberta, they've created short-term exposure limits, and in BC it's 10 parts per million. You can't be exposed to 10 parts per million for more than 8 hours. Otherwise, it's a problem. So that's why it's a problem from a safety point of view. And this isn't just limited to people who are working within the system, within a lift station, wherever. These are obviously built in residential neighborhoods. So if you get bad odors, residents are going to smell it as well. And they generally aren't shy about complaining about stuff like that. So that's one way we know we have a problem. The other thing that happens, and it goes back to that comment about the infrastructure and the asset life, is how does the H2S form? So the previous talk talked a lot about bacteria. So those bacteria that are present in the sewage, they prefer sulfate reducing bacteria. They prefer to feed on oxygen. If they don't have oxygen, then they'll look for nitrates, which is, from basic chemistry, nitrate is an oxygen compound. It's N3 oxygen. If they don't have any oxygen or nitrate, then the bacteria will consume the sulfates that are in that process. And when they consume sulfates, they breathe out hydrogen sulfide gas. And that's where we get the problem. So when the H2S gas is in the water, then it'll move from the liquid phase. Let's go over here. If we think of this pipe here, this is the bacteria layer, this sort of orange layer here. So the bugs are eating the sulfate, they're breathing out hydrogen sulfide. The hydrogen sulfide moves between the vapor and the liquid and the vapor phase. Then because there's moisture in here, this hydrogen sulfide reacts with the oxygen and ultimately we get sulfuric acid. So the sulfuric acid then converts or moves its way through the concrete layer in the pipe, and then ultimately we get the hydrogen or the sulfuric acid reacting with the reinforcing steel within the concrete. So that eats it away. Then you just have a half shell of cement basically with no reinforcement in it, and you get that sinkhole that we showed earlier. So other interesting thing about hydrogen sulfide gas is that it forms different species depending on the pH of the system. So when it's in a pH up to about 7.5, 8, it's in the form of H2S, and that's the odorous form. It does convert into a non-odorous form at pHs above that, but we'll talk later about how getting the pH up to that level can be problematic. And so because of the nature of a typical collection system that typically runs at a pH that's kind of neutral, 6.5 to 7.5 range maybe, that's also the sweet spot for having maximum H2S generation. So what drives hydrogen sulfide in the system? So there's a lot of things that, if we look at this list, that we can't really control. If there's higher BOD or there's higher sulfide levels, we can't really control that because that's a function of the community that the collection system is serving. Hydrogen sulfide is also more prevalent when temperatures rise, because obviously the bugs, they're happier when they're in a warmer environment. They get much more active. Although it's a bit of a misleading thought some people have, I've noticed, because there's a thought that in cold climates there's no H2S generated in winter. And I can tell you, I do a lot of work with EPCOR up in Edmonton, and I see no shortage of H2S in January. It's just nice to deal with inside a lift station where it's at least warm than outside in a manhole. But there is a temperature dependence for sure, because even those levels of H2S we see in Edmonton in midwinter, they also rise dramatically in summer. So those things we can't really do anything about those. We can't control temperature. We can't really control the BOD loading in a residential system. Low dissolved oxygen, that is an issue that can obviously, as we've talked about, make the bugs want to feed on more sulfates. pH, we can control that. Some of these items just down near the bottom of the screen here, we can affect some of these through better like engineering design. So if we have a lot of turbulence in a system, that will help release the H2S that's in the water phase and help it get into the vapor phase. So if we can design the system so that we don't have a lot of drop manholes with big waterfalls of sewage dropping a long way and stirring stuff up, that can help. Retention times is something that, combined with low flow velocities, we can do some things to help that. One situation that I see quite frequently is new systems being built. So, for example, a new subdivision is going up in a community. There's a 20-year design flow rate for what the system is going to look like 20 years from now. But for a bunch of reasons, the system is built with the pump that's sized for 20 years being the pump that's running in year one. So you get, like, for just throwing numbers out, you get 1/10 of the flow that you're supposed to have. So the retention time in that particular pressurized force main goes up by a factor of 10. And I've talked to people a lot about, maybe a better design option is to have a couple of pumps built into the design process so that you switch out a pump after maybe 5 years or whatever. So the whole idea here is to just keep the system moving. If there's the potential for things to slow down and stagnate, then it'll go septic and everything will not end up well. So those are some of the things we can control. So generally, we're stuck with things that we can't control, and how do we mitigate it? And by its nature, a sewer system, it takes organic material from a collection system to a treatment plant or a discharge point at a lagoon. There's going to be odors in there because of the decaying organic material, and generally speaking, it's almost impossible to prevent the odor problem across the entire system. I've never worked in 30 years with a municipal government that had an unlimited budget to do this kind of stuff. So if they did, we could fix everything, but that's not the real world. So how do we try to mitigate these problems in a system? So the first thing that we need to do is understand, like, how big is the problem we have there? I'm sure everyone in the room has had experience with residents saying, hey, it really smells bad. But hey, it really smells bad is hard to quantify. And so to get to the point of actually getting a treatment solution, we need a little more. And the first thing that we can do to start characterizing that problem is get some data. So the first thing that we need to do is let's look at collecting some data about what's the H2S level in that collection system. What does it look like across the whole system? And the way there's a few ways that we can do that. I see a lot of these, a typical transmitter sensor that are fixed units that are installed typically in lift stations and places like that. More prevalent in bigger communities, I would say, because these aren't cheap. They also need a SCADA system to report back to. The other way of doing that is using a remote data logging H2S meter. So we use a lot of those. We just stick those in manholes or lift stations. They can run for a couple of months. And then we can download the data and see what's happening. The other thing we can do is we can do simple wet chemistry test for sulfide, because it's sulfide load in the collection system that's the thing that starts, that's the driver for the H2S generation. So if we can do this simple wet chemistry test. It's very simple, doesn't take very much time. Then we can get a feel for how much sulfide is in the collection system. And then we can also use that, even if we don't know the H2S level. There's a couple of good longstanding references about how we can take the sulfide level, and if we know the BOD in the flow, then we can estimate what the H2S should be later on in that force main, and then we can also figure out then how to treat that. So when we get the data, we're just looking at something like this plot, which just shows here, the blue is H2S, and this is over a couple of week period, and it shows a typical force main in a medium-sized municipality, and you see there's lots of regular spikes, which is just what happens in a collection system over time. It's got those diurnal peaks of flow and everything. And in this case, we see that they've got lots of issues because if we think back to that level of 10 ppm, which is about here, which is sort of a typical control limit, they've got peaks that are way above that. And in this case, their average is, I remember correctly from the data, it's well over 30 parts per million. So that's what we're trying to see. We're trying to understand, what does the H2S look like in that force main over that period of time. So once we know that, then we've got a starting place to start to design a treatment solution. One final thing we can do is we can also take samples, and then we can send those to a lab for a biochemical analysis of the wastewater at that particular location. So you can see here, we've got the typical things, pH, suspended solids, and then we look at the various nitrogen and phosphate compounds, the sulfides, and the BODs. And if we get that at a particular customer site and combine that with flow, then we've got a pretty good starting point for where we can help design what's going on in the treatment system and design a solution to help fix that. So corrosion monitoring. So the other thing, we talked about two things. There's odor and there's corrosion. So we can do all those nice things about odor. Corrosion is a little more difficult to monitor, I would say. This particular picture here is a lift station. It was in a place in Southeast BC, and it's so orange. And this particular lift station, it doesn't have a building over top of it, so it's outdoors. I saw this first, I think it was in November 21, and you could smell this lift station 100 feet away in the rental truck that I drove up in. So they had a lot of odor going on in this place, but it's hard to figure out, how do we quantify that? There are things that, when we think about how to monitor corrosion, there's a lot of techniques around, like dye penetrant testing, X-ray testing, things like that. But those sorts of tests generally involve sending a broken pump or a broken piece of a pipe or something to a lab, and they do the test. A lot of those aren't suitable to bring that kind of technology out to the field. So how do we do that? So I didn't come up with the technique of what I'm talking about next, which is corrosion coupons. It's a way of testing relative corrosion rates in systems that's been used in water treatment for a long time. Typically used in cooling water systems, for example, where if you have a chemical plant and you got a key heat exchanger, you want to know what's going on with the water chemistry and that, but you can't turn the plant off every day to look at it. So if that heat exchanger is made out of copper, then you put in a little coupon of copper in the cooling water, and you can predict what's going on within that heat exchanger. So I thought, why don't we try to do this in wastewater systems? Let's go ahead and install this little piece of metal we see here. It 1/2 inch by 3 inch, just a piece of mild steel. If we expose that in the airspace in a lift station or in a manhole for 90 days, then we can weigh the coupon accurately before and after we put it in. And so then we can calculate a corrosion rate. So no surprise here. It was all nice and shiny and clean when we put this one in. And then when it came out, there was some rusting on it. No surprise. We install these using this PVC little tree here so that we don't just have the piece of metal down there, but it's something that when people are doing other work in the system, they can see the coupon. And a typical example here is just tied to the ladder and manhole, and it's dropped down above the water level. So what we did, we started this in summer of 2021. Since then, we've got 13 systems across Western Canada, and we've got over 100 coupons analyzed. And what we're showing here is what's the corrosion rate that we've seen versus how many coupons there are. So long story short, 70% of the coupons show a corrosion rate of less than 4 mils per year. So a mil is 1,000th of an inch. And the average corrosion rate is 3.7 mils per year. So over time, we do this consistently in a system. So we'll get 4 data points in a year. And what we're developing here is a trend of what the corrosion looks like over time. And what we want to see is a trend that's relatively flat. We don't want to see the trend increasing. And if it is increasing, that tells us something's going on. Why is the corrosion increasing? We need to look at something else in the system that might be causing that. I also have a lot of customers who are starting to get involved with asset management programs. And so we're finding that we can take this corrosion data and the corrosion trends and feed that into asset management programs. Because as you recall, asset management is, it's basically, what do we have? How long has it been there? What shape is it in? How much life has it got left? And what's it going to cost to replace it? So this kind of information can help us give an indication of what shape the system is in and what condition it might be in and how much we might expect it to last. We'll also get back to this in the first case study because we can demonstrate that this is linked to H2S as well. So once we've got this information, we want to treat the wastewater. So how do we do that? So in real simple terms, we've got a liquid phase and we got a vapor phase in a collection system. So there's a bunch of techniques we can use here: nitrates, oxygen and air, pH, oxidizers, or precipitation. Those are things we can do to treat the liquid phase of the wastewater system. There's also the vapor phase. One thing that we see a lot is carbon, which is an adsorption process. So just take activated carbon. If you run air that's got pollutants in it, like H2S, the activated carbon can just remove that. There's other things that we can do on the vapor phase as well, like biological treatment, trickling filters, things like that, chemical scrubbers, and then dispersion, which is really just getting big fans and blowing the nasty air far away, and it's not a problem. At least that's what some people tell me. So one of the treatment options is one of the products that our company supplies called Oxinate. It's a calcium nitrate product. So what we do with this product is we just feed it into the collection system. This is a typical feed setup, not only for Oxinate, but for most other chemicals. A couple of dosing pumps, a storage tank, some instrumentation. It's very cost effective. Calcium nitrate's also non-hazardous, doesn't require any specialized handling, which is not something we can say about some other chemical treatment options. But What we see with oxygenate is when we have a system that's kind of out of control, we can start feeding it. And usually within 24 to 36 hours, we can eliminate the H2S activity. And it's pretty easy to get to 0 ppm of H2S. Then what happens is people tell us we can't afford 0. So how much does it cost to get to 10 or 15? So we can get to 0, and then we spend a lot of time working our way back up again. Oxygen. Oxygen is a good way of creating aerobic conditions in a sewer, in a collection system. If we keep the system aerobic, we'll never have H2S, but there's a few problems with the with oxygen, in that you have to store liquid oxygen on site, so that can be challenging. The other problem with oxygen, and with the next one I'll briefly talk about, is how do you inject this into the wastewater? So you've got to diffuse it into the wastewater so that you don't get a lot of turbulence. That can be disruptive and generate more H2S, kind of counterintuitive. I'll just go through some of these other ones fairly quickly. So there are ways you can inject air. If you don't want to inject oxygen, you can inject air, but on a volumetric basis, air is a whole bunch of nitrogen. So to get the same amount of oxygen, you got to inject 5 times the amount of air as oxygen. Same things apply with, you know, the energy demand, the turbulence, and all of that. We briefly touched on earlier controlling pH. It's totally possible to do that using these basic chemicals, either caustic, magnesium hydroxide, lime, calcium hydroxide. They act really fast. The only problem with those is they're not very cost effective. And if you're raising the pH to get rid of the H2S, pretty much in all cases, you're going to have to reduce the pH again before you get to the wastewater treatment plant. So you got double the fun in doing this option. Oxidation, similar kind of thing. You can take these oxidizers, chlorine, hydrogen peroxide, for example, and you basically are burning off the sludge layer in a pipe. So if there's no bacteria there, there's no bacteria to breathe out hydrogen sulfide. The only problem is the bacteria don't get the memo that they were burned away. So once you burn them away, they come back again. So you have to keep burning the thing off. Chemical precipitation, that's another option. Iron salts react with sulfide. So ferric chloride, ferric sulfate, you can feed those and just get rid of the sulfide completely. They're not the nicest chemicals to deal with. They do have some benefits in the treatment plant for primary settling, for struvite control, but they are hazardous. They also tend to stain things like ultraviolet lights. Just briefly on the vapor phase, this is a typical manhole filter that we see and have installed for customers. So it just fits into an open manhole. This bucket here is filled with activated carbon. So any odor that flows up through the sewer goes through the activated carbon, and we're done. That's just a bigger version of what's going on. To that one is filtering the air in a lift station as opposed to just a manhole. So how do we choose to control H2S? So ultimately what we see here is everyone's got various factors. So system characteristics, budget, staff, what instrumentation do we have? What's the wastewater look like? And ultimately we're looking for the ultimate ideal H2S control right in the middle that takes all of those factors into account. So I notice I've been talking too much on the boring stuff, so I'll get into the case studies real quick here. First one is it's a rural county in southern Alberta. It's very large. It's also got a really long collection system, like with one force main that's about 54 kilometers long, with 3 big lift stations. So they have they have some retention time issues here for sure. when I first got involved with this account over 2 years ago, they had really bad control, and they were suffering from a problem that a lot of people I've noticed have, which was the operators that I started talking with were 6 operators removed from the person that actually set up the program like 6 years ago. So they had no idea why they were doing what they were doing. Just someone told them to do it and they were doing it. So they were feeding the same amount of chemical all the way across the system, and it made no sense to me, and their results were horrible. So 2.5 years later, we did a lot of measurement with them and got them to do a couple of things. So we changed how they fed the treatment product. So they now feed it based on flow instead of just a certain amount all the time. That made a big improvement. And then one thing that I've noticed is control tends to improve in a system when you start to pay attention to it. Even sometimes without making any changes, it seems to happen. It's kind of neat when that happens. So what we see here, this is just a summary of the results. So the green bars here are the corrosion rate in the system that we've measured on these corrosion coupons. And this orange line, there's a gap here because of a meter problem. That's the H2S rate. So what this shows is that the H2S level and the corrosion level are linked. And that's, I would have expected to see that, but it's also nice to see this proven in full scale. And why this is important is this is a big system, big county, lots of budget and everything. There's a lot of places that can't get into a big data monitoring program and everything. So we can use these corrosion coupons, and you can see, just as an aside, how the first coupon that came out, it didn't look that great. It was kind of black after it was cleaned up. The last couple of coupons, especially this one last fall, look almost new when they came out. So we can apply these corrosion coupons in small systems as sort of a passive H2S proxy for what's going on in the system. So that was really interesting to be involved in that. The final one, I'm going to go through, I'm just going to scroll past that one because it was much the same, and just talk about really quickly about lagoons and wastewater treatment. So a lot of our customers discharge into treatment lagoons. They also have H2S problems in those lagoons because sludge builds up. It's the same chemistry as in the collection system. And the best performance that we see in a pond, we should have a dissolved oxygen of at least 1 milligram per liter or more. And we should also see a pond that looks like a pond, not like a really dark, nasty mess. No surprise, the ponds that are dark, messy, are anaerobic, they have odor problems. So that's a bad pond. That's not a pond color. I mean, it is, but it's not, and no surprise that this pond just absolutely reeks. This is a pond I saw in April in northern Alberta, and it was hard to believe it was a wastewater pond. It was amazing. So what we do and have found effective in a lot of these ponds is we can also, we have a chemical treatment that we can apply with the calcium nitrate. We can also aerate the pond just to maintain dissolved oxygen. Dewatering the pond can help. I've had customers tell me when I asked, so when did we last dewater the pond? And the answer, well, we've never dewatered it, but it's like 20 years old. And no surprise, now it's got capacity problems and odor problems. You think, I think I know why that is. And so with some of these simple treatment things, we can test for dissolved oxygen. We can test for nitrate if we apply nitrate to it, and then we can get good results. And I just wanted to show finally, this is a simple aeration solution that one of our customers did, because people say, oh, that costs a lot of money. So all they did is got a couple of sprinklers and recycled water from the pond and sprayed it on the pond, and then had a pump that they again, they recycled just from in the pond and just recycled the water back underneath the surface just through a fire hose, like really simple aeration, really simple solution, and it worked. It was awesome. So finally, I'll just end by saying, when you have odor and corrosion problems, do you have a problem that you should care about? Is there an issue here? Do you have odor complaints? Do you have older infrastructure? I would argue just about everyone that I talk to, the answer to those two questions is yes. And then how do I solve that problem? And again, I think the quickest way of solving that problem is to go through an assessment process to kind of quantify what you have. And then there's treatment solutions, a variety of them that we can apply to help fix that problem. So thank you very much. Again, apologies for no in-law references, but that's something to think about for my next presentation. So thank you.
Give me some questions.
Sure. Yeah, happy to.
Okay, so we'll open the floor for some questions, and if we have any online, we'll get to those too. Any questions here?
We were going to get away with it.
That's right. I'm just wondering, with the sulfur forming bacteria, when you're putting in the calcium nitrate, is there a ratio that you're looking for? Or when you said like you look at flows, is that like what are you testing for to see what type or the amount of calcium nitrate that you're putting in the system?
So there's a couple of rules of thumb that evolved out of some theoretical research, that so much nitrate per sulfide level. I can't remember the exact number. I remember it in I think it's like 2.1 milligrams per liter of nitrate to 1 of sulfide. I think, don't quote me on that number. I have it in a spreadsheet that's in more useful things, like how many liters of this for what. So I can, basically the idea is to take the results from a lab and be able to plug that number in, and then say, oh, we need this much. And so it starts like at a theoretical basis, and then it's a question then of how much does the customer want to spend? How much can they spend? What level is acceptable? I can tell you that I have a range of customers, and people have a very widely spaced tolerance for H2S. I have some customers we've been dealing with that have had, for example, had a broken lift pump in a major force main in their system this summer. So it's been hard to treat that system because we know it's broken. And in the last few weeks, we've been talking about, hey, you've been able to reduce your H2S from 400 to 200. That's awesome. Like, it's not, because 200 is awful, but it's relative, right? So it's a question that we get a lot. And the answer is really, it's part of a conversation, right? Because I can tell you probably what we need to feed to get to zero, but I can also tell you don't want to pay for that. So, it's usually, many of these treatment decisions they're like a spectrum, right? There's more than one way to fix the problem. And we just talk about how with nitrate, that might be a good example, or a good option for some people. Maybe oxidizers are a good option in another place. It depends on, every system is different, but does that help? Okay.
Any more questions? And none online? Okay.
Awesome.
All right, well, join me in thanking David for coming out.
Thank you.
Thank you, sir.
You should get right on. Thank you.
Thank you. So a little 15-minute break. We're back at 3 for our final session in the wastewater stream.